thank you so much for the introduction, and it's been very pleasurable getting to know some of the students in my meetings this morning and seeing some familiar faces in my meetings after that. I wanted to talk today about a topic which has taken me down a path which is somewhat different from my previous research efforts, which have been mostly focused on trying to discover methodology and validate that methodology on data, where the methodology is to classify, to predict, to forecast, to estimate a parameter, and so forth. So this is different in that we're trying to basically solve a problem, a sort of a meta problem of estimating performance directly from data. What performance? The classification error that a Bayes classifier, a minimal probability of error classifier, would exhibit if you could somehow construct that classifier. But all the while, estimating its performance without actually ever constructing the classifier. So we call this learning to benchmark. It's useful, as I'll explain later, in a variety of problems involving experimental design, problems in stopping, knowing when to stop sampling or stops training a method or a procedure, and more generally, looking at sort of the fundamental value or quality of data, right? Independently of how much cleverness you have in putting together a good algorithm for classifying, predicting, or forecasting. Okay, so this is based on a paper that was recently submitted to JMLR, and it's on the archive if you're interested. Just acknowledge the students, my co-authors on the paper, and other students who have had a role in taking me down this path. Okay, so we'll talk about what we mean by benchmarks, talk about how this can be mapped directly into a problem of estimating an information divergence, Ali-Silvi measure of a difference, similarity between distributions, and then talk about some methods for estimating this divergence, which now, of course, is estimating the benchmark, since we have this equivalence between benchmarks and divergence measures, and then a few applications. So, there, that should, I don't know. Okay, so benchmarks have their basis in the following problem. Let's say you have a data set, you want to approach that data set with a variety of methods for, say, classifying multi-class or binary class classification. And so you can implement a k-nearest neighbor classifier, probably the simplest prototype classifier around, right out the box on these three classes. You can maybe go to a support vector machine. You can go to a convolutional neural net, or a variety of other types of methods, right? Bayesian methods, HDPs, logistic regression, whatever your favorite method is. The issue is, how do you know once you've compared performances empirically on your data using a training, validate, and test set? How do you know that you're really you're pulling as much information out of that data as is possible? And so, just an illustration of this is just a picture I took out of a recent paper by a group at University of Washington, computer science, for the Mnist digit data set, where they proposed yet a new variation on a neural network based on the olfactory system of moths. So basically emulating a 4 hidden layer neural net of a moth, and they claim that they do really well over a range of training samples per class. The real question that we're trying to answer is one that is encapsulated here, Andrew Ng's blog, on what is the benchmark? Is there a maximal accuracy that one can squeeze out of the data? And if so, can you somehow estimate that? And of course, we all know, being trained in statistics, that there is a Bayes optimal bound somewhere if there are priors on the classes and the data is coming from some set of a family of distributions conditioned on each class. And so what the objective is to estimate this Bayes optimal accuracy, the minimum probability of error, but based directly on the data, not having to go through actually implementing all of these structures. Right. So predicting performance is nothing new, right? I mean, you can go back at least to the early 19th century with design of experiments and look at the various developments that occurred in optimal decision processes, model selection. All of these involve predicting performance in focusing on the performance aspect, how well can you fit the data in order to, say, choose a set of sampling points when you're trying to do polynomial regression like Gorgoni, or like Sutton and Bartow, model-free prediction of performance, so that you can decide under a particular action what performance you can expect in the long term in terms of say, maximizing a finite horizon value function. So estimating or predicting performance is a classic problem. The issue that we're facing is we want to do this in a model-free way. So the question then is it possible? Well, this sort of gives an inkling for why one might have hope that it's possible to bypass the model, bypass the optimization of training a neural network, or of implementing an HDP, or of optimizing over the various tuning parameters some complicated regression model. And that's this remarkable work by Jared Friedman that looked at constructing a multivariate runs test for testing whether outcomes available in two data sets, the green and the blue, came from the same distribution or different distributions. So on the left, we have two very different distributions. On the right, two distributions which are comparatively closer to each other. And so the Friedman-Raski test statistic is basically the statistic that counts the number of what are called dichotomous edges in a minimal spanning tree that spans the union of all the points in your two classes. The dichotomous edge of the minimal spanning tree is in this case the only edge which connects two points of opposite classes or of different classes. And so there are more edges in the case where you have closer distribution. So the more the edges are, the less discriminatable these two distributions are. And it turns out that in a follow-up paper by Hemsey and Penrose, that they proved that this number of dichotomous edges statistic under some assumptions on the distributions and on the realizations from those distributions being IID that this converges to a bound on the Bayes error. And so one can get a bound on the Bayes error by simply constructing a minimal spanning tree over your data set, right? And how tight is that bound? Well, that depends on the underlying distribution. So what we're going to show in this paper, in this talk, in the paper I just showed, is that one can find unbiased, consistent, and in fact, optimal rate estimators of not a bound in the Bayes error, but the actual Bayes error, without ever having to construct a classifier. So the classification problem, just to set up the notation, you have a label, Y, and binary label we'll start with some prior probabilities, Q and P, for 0 and 1 respectively. There's a observation that could be multidimensional, but has a distribution, a multivariate distribution, which is either F1 or F0 when label is equal to 0 or 1 or 0 respectively. And so the Bayes optimal classifier, we can write that down, right? Given that we have this model, the average probability of error is minimized. The 0-1 loss, the average 0-1 loss is minimized by the maximal posterior mode of the distribution constructed from this model description of the conditional distribution of the observations and the prior. Okay, but we're interested in the error rate, not in the classifier, right? So what's of interest to us is this quantity, this epsilon, which depends on the prior probability of y equals 1, class 1, and depends upon, of course, the distributions, the conditional distributions under the two labels of 0 and 1. And it's simply the probability that the classifier gives us the wrong answer, right? C of x is mapped to something other than the true label of x. Well, this has an integral representation that one can very easily in 2 lines write down in terms of an integral of the weighted difference between the two conditional distributions, or you can look at the difference between the two non-conditional distributions, the product of the conditional and the marginal. And then there's some weighting factors and scale factors and so forth. So there's an integral representation. So what it boils down, this problem of benchmark learning boils down to coming up with a good estimate of this epsilon quantity. So an alternative representation turns this epsilon into a F divergence. So a definition of a function g, which is given here, convex function equal to 1 when u is equal to 1, 0 when u equals 1, and this then gives you a F divergence as defined by Jazar or Ali Silvi, which we can now categorically state that bounds and representations of the minimal probability of error, that is the Bayes error, can be expressed as an F divergence. And so that's important because what we're going to bring to bear are general tools for estimating F divergences from data. So some examples are the Shannon F divergence, the Kovac-Leibler using the log U, as Shannon did in his definition of entropy and mutual information, the Renyi entropies and Renyi divergences. Right. Total variation distance is another definition, which simply is also an F divergence. The alpha divergence, which I just mentioned, the Kovac-Leibler divergence, which I just mentioned, the Hellinger-Bhattacharya distance, which is another form of F divergence, simply the L2 distance or L2 squared distance between the square roots of the conditional distributions. That should be F0, F1. For why I wrote F1, F2 here, but just read this F0, F1 for these quantities here, a change notation. Some other instances of great interest is, in particular for this talk, is the generalized total variation distance, where G is that function that I just described, which gives back our Bayes error, right? Our minimal probability of error, attainable by any classifier with specified priors and specified conditional distributions. And then there's the Henze-Penrose divergence, which is, this is the divergence quantity that I mentioned before in the context of that Friedman-Brasti minimal spanning tree dichotomous edge count runs test. This Henze-Penrose divergence, as I said, gives a bound on the minimal probability of error, the exact representation given by this generalized total variation divergence. And the Biota-Carré bound, of course, bounds this epsilon. Epsilon PQ is the same as epsilon P. Minor change of notation. So learning to benchmark reduces to F divergence estimation, right? Henze-Penrose bound on the actual minimal probability of error is generally a tighter bound than the Biota-Carré bound, at least for equal likely classes. All right, so now that we have this equivalence, the question is, how do we go about empirical estimation? How do we construct a good estimate? Well, this really goes back to the issue of estimating functionals of densities, right? Because that's what the divergence is. It's this integral of a function g, which may or may not be smooth, as in the generalized total variation distance. It's not smooth, but it depends upon F1 and F0, the conditional distributions under the two labels, 1 and 0. And so density plugin estimators basically will define density estimates, kernel density, or histogram, other types of estimates, plug them in, and then either do this integral empirically through a summation or Gaussian quadrature or whatever the method that with a kernel density estimate, you might use Gaussian quadrature. With a histogram type estimate, this turns into a sum. Okay, so what's the issue here? The issue is that we know that density estimation is hard, right? It suffers from exceedingly poor statistical convergence rates, right? So the root mean squared error decreases very slowly in the number of samples, typically on the order of n to the 1 over n to the power 1 over 2d, 2d the root of n. And of course, optimal parametric rates, which are typical when you're estimating scalars like this epsilon quantity, this benchmark, have parametric rates of convergence, right? So how do we get around this issue of really, really slow convergence so that you need tremendously large sample sizes in order to accurately estimate these performance measures? Well, the answer is we're going to go, that's the next segment, we're going to bring into the picture a particular type of ensemble technique, like boosting technique, which uses weighted ensembles of base estimators, of density estimators, as they're going to turn out to be, with different resolution epsilon. So a kernel density estimate has a width parameter, epsilon, a histogram parameter, a histogram has a bin cell width, and so forth. And so we're going to take various bandwidth parameters, define estimators of this divergence, the benchmark, and then we're going to take a weighted combination, a linear weighted combination, to form an ensemble estimator. So while each one of the base estimators suffers from this punitive 1 over the 2d root of n, which is almost logarithmic in n, right? In terms of its rate of decrease for large d, for large dimension, feature space. We can combine these so that we get parametric rates. That is the key. And we combine them in such a way that we can, turns out, compute these weights offline. W0 can be computed offline. So this just is a picture showing what I'm talking about. You have these bandwidth parameters, which I'm now calling L1 through L sub capital L. Each forms a base estimator with a particular bandwidth on the density plugin. And then you take all these estimators, you plug in some weights computed offline, and then you sum those over the class of the ensemble base estimators, right? And that gives you an overall ensemble estimate. So this is a method which is reminiscent of boosting, like Eta boost, that was shown by Friedman, Hisey, to Pedrani to be equivalent to an adaptive logistic regression method. And the issue with these boosting methods has been that they use data-dependent weights, even though they can achieve under some conditions, as shown by Peter Bilko and Reitov, that they can attain Bayes optimal performance. We're going to give an alternative, which is going to specify a set of weights that are not data dependent, therefore that can be computed offline by solving an inverse problem, by solving a linear program that gives us great optimal weights. That is, weights that will lead to an ensemble benchmark estimator, which has 1 over root n, root mean squared error, as a function of the number of samples n. So we can. The question is, what kind of base estimation methods can we use here for each one of these component weak learners or base estimators of the benchmark? As I mentioned before, one can use kernel density estimates. We have a paper using one of our papers that proposed this in 2012. You can use epsilon ball and nearest neighbor ratio estimates. You can use locality sensitive hashing. There are lots of different base estimators. And I'm just going to introduce this using the locality sensitive hashing plugin estimator. Locality sensitive hashing in this context is nothing more than a histogram estimator, plugin estimator of the distribution of the blue and red distribution, where MI and NI come from respectively. And so you form a histogram estimator. These cells of the histogram are those for which they contain at least one blue outcome. So the blue class has at least one outcome in each one of these cells. The other cells that don't have blue outcomes but may or may not have red outcomes, we throw away. So that's why we have this summation over MI greater than 0. And so this looks like a terribly biased estimator and a very simple one, where you look at basically the ratio of the histograms over these regions, these cells that contain both blue, well, contain at least one blue point. The point, though, is that it is a pretty terrible estimator for a particular edge length or bin width epsilon. But if you take a bunch of these for different widths and you use just the right weights, you can get a really good estimator of this divergence function. So how do we do this? Well, we have to, the problem is that we suffer both from bias and variance amplification due to the fact that we're estimating these densities. So we have to quantify the bias and we have to quantify the variance. Well, the bias it turns out, well, as you might expect, we want to make the bias decrease as 1 over root n, right? So if you do a simple analysis with, an asymptotic analysis, Taylor with remainder of the bias function associated with the divergence estimate, then you're going to get this is the base estimator with a particular epsilon, a particular resolution. Then the bias, it gets better as the resolution gets better, but as a function of n, it's an epsilon, its decay is very poor. So the variance of the hash-based estimator decreases as 1 over n. So in order to get a root mean squared error decrease, we would like to equalize the rates of decrease of the variance and the square of the bias. So how do we do that? Well, we'd want to choose epsilon in some optimal way. If you choose epsilon so that you get this remainder term equal to 1 over root n, so that means that epsilon is going to be equal to 1 over n to the power of 1 over 2d, right? To get this go to 1 over root n, well, then that's going to force this remainder to be 1 over root n, which is great, because now we'll have the remainder term of the right order for parametric rate. But we have all these terms up here, which unfortunately the leading term, the slowest term, is of order 1 over the 2d root of n, that terrible rate that we had before. But here's the trick. If we now have several of these estimators, these base estimators, each one at a different epsilon, if we choose the epsilons judiciously, and then we take an average of the bias over those different epsilons, the average is not going to be affected by these coefficients CI. What do these coefficients CI depend on? They depend on all the stuff we don't know, right? They depend on the Taylor series expansion of the divergence that is about epsilon, which controls the f hat 1 and f hat 0. And so those depend on the unknown densities, right? The unknown conditional densities. So if we take an average of this bias, and the average only affects this epsilon because we're averaging not over I, but over L, right? Epsilon L, then we have a hope to be able to maybe even knock out this term by using the right set of weights. Okay, so that's what we do. That's what this ensemble bias reduction story is about. We choose L-based learners, as I said before. We're going to choose epsilon so that they're all of this with this rate minus 1/2, 1 over 2d, I should say. And we have a parameter t that's going to be a design parameter. It's just a set of scale factors. So this is a set of bandwidths, all of which decay at the same rate, but that scale linearly. So the bias of the divergence estimator is just as I said. You have now this sum over the weights, over the TJs are the only thing that depends on J. Now T is indexed by J, indexed from 1 to L. We have this remainder term of 1 over root n. And what is this? This is a sum of L terms. We have a set of linear equations. It's a linear system of equations. We have D of these equations, L variables. So that gives us this linear set of equations. If we can set that equal to 0 by choosing these weights, then we will effectively have knocked out the leading bias term, and we'll end up with this parametric rate of decrease of bias. We know that the variance decreases as 1 over n, and so then the root mean squared error will be parametric in its rate of decrease as a function of the number of samples. And the way we choose these points t, I'm not going to go into that, but we use a Chebyshev approximation method to choose these scaling factors. Okay, so the estimator variance, of course, may blow up if we use the W, the weights that give us the solution to that equation that knocks the bias out. The variance will increase. So we really need to use enough degrees of freedom, enough weights. L has to be greater than D in order to be able to both zero out this set of bias terms, but also to minimize a bound on the variance. So the variance bound has a simple quadratic form, defines the variance, and so you simply bound that by the maximum eigenvalue times the norm squared of W. So what we have is effectively a linearly constrained quadratic program that the constraints, again, are going to set the bias term so that it's 1 over root n, and then we're going to minimize the bound on the variance. So this will ensure that we get a parametric rate. The weights are computed offline. There's Wj, that the TJs are the Chebyshev polynomial roots that have nothing to do with any densities. They just have to do with a polynomial a Chebyshev polynomial approximation to a universal approximation problem, classic Chebyshev solution. So how does this work? Well, we have some simulations to show that we're actually have a benchmark that becomes increasingly close with confidence intervals here that are, in this case, bootstrap confidence intervals, to the true Bayes error, which is down here. This is for 4 classes for a nonlinear classification problem where each class is in a spherical, concentric spherical ring that over 20 dimensions. So we can see that you use a random forest or a deep neural network. They're always above the bound. The deep neural network happens to come closest after 5,000 samples, and so you know that for at least for this case, this deep network is coming close to the bound. Another application is as a stopping rule, where if you have something like an eta boost method where you're selecting over the sample size, selecting successive samples to use to iterate over the eta boost optimization routine, then you have, this is a bound. This is our Henze-Penrose bound. Here's the benchmark in blue. Here's the truth. In this case, for 2 classes, shifted Gaussian densities over 10 dimensions. This tells you, it gives you a stopping rule. When you start to become within epsilon, within some percent of the benchmark learning predicted error, predicted minimum error, then you can stop the eta boost algorithm. So it could give a stopping rule that way. It can also be used for the sort of the social good, where the society I'm talking about are those in machine learning who are rushing after incremental improvements on being able to classify these canonical data sets like Mnist with 10 classes, large dimensions, 60,000 samples. And so you can implement the benchmark learner on this data, and this implemented in this case with an epsilon ball estimator, and you get that the minimum achievable error rate is about 14%. I haven't given any error bars here because we're so far away from the actual error rates that have been reported, at least up to a few years ago. So this tells you that there's significant margin. Another application, which is kind of fun, very recent, unpublished as yet, is one problem in computer vision, which is of great importance, is recognizing humans and recognizing where they are in an image. This is a 360 degree image mosaicked from a sensor on so-called Jackrabbit, which is collaborators Silvio Savarese, who's a CS computer vision professor at Stanford. So we took his data, and he wanted to know just what is the achievable, minimum achievable error that I can obtain on detecting people. If I have a computer vision system that draws bounding boxes around objects, like you can see here, what is the achievable error once you've drawn those bounding boxes? Some of them will be people, others will be tables, and who knows what else. So we ran our benchmark learner on this to find the minimum probability of error estimate to see if we could give Silvio Savarese a benchmark. And so the issue here is that there are 28,000 bounding boxes that contain people. Each one varies by a factor of 10 or more about the mean size. And that's simply because some people are far away, some people are close to the camera. And so that we don't have the same dimension. So what we do is we form a 1,000 dimensional representation through ResNet 100 autoencoder. That's standard in computer vision for representing these bounding boxes. It's 1,000 dimensions. And then we use a ResNet 32 classifier on this 1,000 dimensional data set now to predict the improvement that's possible. And as we find, there's about a 30% possible improvement over what the state of the art is. We can also show this picture. This is just looking at the PCA subspaces of this D-dimensional down to the first 12 dimensions. Two things that are interesting. The first is that, and we don't understand why this is yet, is that the probability of error, the Bayes probability of error, is decreasing, of course, as a function of PCA dimension. You're including more and more information, but it seems to follow very closely the trend of decrease of 1 over r squared, right? The amount of residual error that's explained, right? That's r squared. So we don't understand why this is, but this is a very intriguing relationship that we're currently studying with Silvio. We can also, I'm also showing a basic resampling histogram that so you can get some idea about the uncertainty about the mean error rate that would be reported by the benchmark learner as a histogram about, in this case, is the 12-dimensional histogram about 0.158 with 12 dimensions. Another example I want to show quickly is one that actually represents a collaboration with Peter Song, which is benchmarking mobile health predictions. So here we have a number of subjects. There's in a flu virus challenge study. Here are two subjects here. They're wearing wearable devices, Empatica E4s, which measure heart rate, accelerometer activity, that is skin temperature, and electrodermal activity on the skin. And this is over a period of about 7 days, over which this challenge study with 39 subjects enrolled these subjects where they were exposed to a virus at 34 hours. Is a flu virus. So you have a before and after, a baseline, and then after the virus. This particular individual was not infected, didn't get sick. This individual did get sick. So the question is, based on this data, can we describe how well we might be able to predict whether or not a subject might get sick or not, right? Just based on observing, say, their baseline data up to the point where they start shedding. So the first 60 hours. This is the shedding. Shedding is, of course, an indicator of viral infection. And so this shows sort of the balance of shedders and non-shedders. It turns out there's only 20 subjects who had usable wearable data. So this really is only 20 subjects. This is the subjects along with their shedding profiles. So you can see subject 2 has intense shedding at about 60 hours. This is relative. 0 here is equal to 34 hours. And so this is around 60 hours. There's high amount of shedding on subject 2, no shedding on subject 1. So we derived 12 statistical features, mean, median, and standard deviation over 10-minute epochs or intervals of these signals. This is, I'm just showing the heart rate, median heart rate for the non-infected versus the infected individual. You can see very, very different profiles after exposure. The infected individual has some trend where their heart rate is steadily increasing. The blue is a segmentation into a sleep versus wake, which I'm not going to talk about because I'm not going to present results for that. What I'm going to show is what is the feasible prediction error of infected versus non-infected if you have the first 60 hours of data, and this data. So 12 statistical features, and there's just a plot of 2 of these features that I won't mention further. So we're looking at then the first 60 hours, day 1 and 2, and we have 4,000 samples. We're going to look at, basically the model is you take a sample, and that sample is independent of all the other samples. Perhaps dubious assumption because there are only 20 subjects in the study, so some of the samples may be from the same subject. But nonetheless, we can use it to construct a benchmark prediction. And benchmark predicts that, well, you can really only get up to accuracy of around 78%, well, 77.25%. If you implement a random forest on these first 60 days, all these samples either from class 1 or class 2, so granted there's a lot of variation. We're not using any type of time series model here. You only get up to 35%. So it says, well, you can predict, the benchmark predicts we can reduce this by at least 25% if you're going to use a aggregated predictor that aggregates all these 60 hours together. Then this gives the histogram about this number that I just quoted, 22.75, fairly tight, as you can see. That gives us solution. So I have about maybe 5-10 minutes left, and so I'm going to switch here to another application of this technique. We're not going to be trying to learn a Bayes minimal probability of error performance benchmark. Instead, what we're going to do is we're going to try to learn about deep neural networks, in particular the information bottleneck. And so how can we apply our methods to this? Well, it's going to boil down to estimating a divergence, which is the mutual information given layer relative to the input and the output. So we all know deep neural nets have really good performance. We don't have very high understanding of why they perform so well. There have been some hypotheses that have been put forward about why they work so well. One of the hypotheses that's relevant here is the compositional learning hypothesis. It basically says that when you train deep neural networks, they learn the same way that children learn, that they learn in 2 phases. They first learn the easy cases and memorize them, like a child learning how to speak. And then once they have enough syntax and enough knowledge of the semantics, semantical structure, they start to generalize and can speak and effectively describe much more complicated patterns than you could just by memorization, right? So this is called the compression phase in this compositional learning hypothesis, since they're stopping their memorization. They're not just memorizing everything. They are compressing that information so they can make sense of it and use that to construct the concept or the class predicted by the convolutional net. So Back in 2017, just a few years ago, Naftali Tishby and one of his collaborators at Hebrew University, or Schwartz Siv, proposed that the information bottleneck confirms this compositional learning hypothesis for deep networks. And the way they did this is they looked at it at the encoder and decoder of the network, as encoder is from the input to a layer, internal layer, say TI, and then from that layer to the output, they call the decoder. And what they showed was that if you plot the mutual information, or the nonlinear correlation between the input and a particular layer T, and plotted that against the mutual information that the output has on relative to that layer T, you get a set of curves that look like this. These curves are start at 0. This is initialization, and now you start training the network by presenting more and more examples using stochastic gradient descent, and you eventually converge each layer. Here there are 5 layers. You eventually converge to the a very high information about the label, right, at every layer, and a very high compression of the data, right? So there's a memorization phase where the mutual information is between X and T the entropy is increasing. You're memorizing the data, and then you go back to compression, where the mutual information effectively decreases between the input and the layers. And so mutual information is a divergence, so we can apply the methods that we mentioned. So this was actually a very controversial claim, and there were several other papers that came out in the ensuing year that challenged this on the basis of the fact that they only demonstrated it for an inverse tangent nonlinearity activation function, and that they weren't using the state-of-the-art methods for estimating mutual information. And so this group here, David Cox, a computer scientist at Harvard, published a paper where they said, well, you know, this compression this memorization followed by compression really doesn't hold for the internal layers. These are internal layers here. That's the input layer. For the ReLU or for the inverse tangent, but especially for the ReLU, the nonlinear rectified linear function. And so this is not a universal result that this compositional learning hypothesis is valid for all learning deep networks. So what we decided was let's jump into the fray at considerable risk, of course, and see if we can maybe contribute to this discussion. So Sachs claimed that there's no compression. This memorization compression idea is really not universal. And so the first thing we did was we implemented our rate optimal estimate of mutual information, divergence, for these two measures of mutual information from the input to the output, and from the input to the layer and the layer to the input. And we have a much smoother trajectory through the epochs of training than the Tishby's method, which used a single histogram estimate to estimate these mutual information quantities. So much more stable ensemble method than the original method. And then when we looked at these information plane, what they was called, we see that we have this memorization compression phenomenon that does appear. So if you use these rate optimal methods for estimating mutual information, you bring out this confirmatory evidence that the compositional learning hypothesis is perhaps actually true. So summary, main takeaways here is that there are really two types of meta learning that's going on here. One is learning ensembles, which is used to implement a rate optimal parametric rate estimate of the benchmarks of mutual information of any divergence measure between distributions, and then learning the Bayes error rate, learning how difficult it is to learn, basically, is the second type of meta learning interpretation you can ascribe to this work. The epsilon ball or LSH ensemble method is one way to implement these approaches, and we showed this for several learning applications. So I think that's all I have. I thank you for listening, and be glad to entertain any questions that you might have. Thank you.
Thank you so much. I'm sorry, I'm going to leave my video off because my internet is unstable.
Sure.
I know it's not as good to have a sea of black boxes. So we don't have anything in the chat now. We've been starting this tradition of taking a 5-minute break at the end of the talk to let everybody stretch their legs and get some water.
Yeah.
So maybe we will do that and reconvene here at 4:30 for questions.
Sounds good.
All right.
All right. See you then.
Hello.
Hi.
If folks are ready, we can come back for the Q&A part of the talk. I guess I'll give other people a chance to ask questions if anybody has any questions that they'd like to ask. Okay, if not, I have a question.
Sure.
My apologies if this was covered. I missed, I think, the interesting middle bit of your talk when my internet failed. So,
Oh, I'm sorry. Yeah.
it's recorded, so I'll go back and look. But I was wondering if you have applied this to questions of, does an additional data source or an additional piece of information contribute significantly to your predictive capabilities?
Yeah, that was one of the motivating applications, was indeed to look at the value of data, value of variables, right?
Mm-hmm.
So, what we've been able to show that for certain problems, certain types of divergences, at least in the asymptotic limit, that you can apply a kind of a greedy selection mechanism of submodularity. Mutual information is one of those quantities that satisfies this property, so that you can basically rank every particular modality or variable in terms of its relative influence on error, right? On reducing error. What we're still struggling with is applying this to the actual Bayes error, because that we've not been able to show that that's submodular. So we would need to, that is submodular in the number of variables, or in the sets of variables, I should say. And so without that, we're basically forced to fall back on enumeration, right? So we have to evaluate these benchmarks for every possible subset of the data in order to evaluate, the value of that data, rather than just pulling one data point out, finding the most informative single variable, then adding the next most favorable supplement to that variable, and then going until we exhausted all the variables. That turns out to give you a guarantee that you'll be within sort of the 1 over E, the Eulerian logarithm of the enumerative set of variables that maximize gain in performance.
I see. But even the ordered approach, I think, seems very useful and promising for a lot of applications where, you might have some other ordering besides utility, like cost. Some things are just very easy to measure, and we always have those. And then does it make any sense to add this extra expensive assay or something? Yeah. That seems very promising.
Yeah. We did have a paper that we published, I think a couple of years ago, where we applied this to a navigating robot. And what we wanted to find out was, what's the value of all the sensors? So this robot was fitted with dozens of sensors. And we wanted to figure out, if you could reduce those sensors, which ones would you want to take away, right? Mm-hmm. And by using this method, we could go back to all of the data that had previously been collected by that robot, and then just prune off different sensors, evaluate our benchmark method, and then figure out when does the sensor that the next sensor that you remove really start to send the performance down the hill, right?
Very cool.
Yeah. So one of the primary applications, and it's really was actually probably one of the main motivations for developing this.
Mhm. Are there other questions?
Hi. Very nice talk. Great work. So I have a question regarding to your comparison in the Mnist data set. So I think you make a table there and compare all the different methods with different, very small classification error rate, right? So I think your benchmark learning give the smallest classification error.
Right.
Yeah. So that is very encouraging results. So, but my question here is that did you use all the training and test sample to get this error rate, or you only use training sample? And I think for all other methods, they basically train their classifier using training sample and test. Get this error rate from the test sample. So how do you kind of see this comparison, whether it's a fair comparison or and also another question is regarding to whether you can give the standard error of your error rate estimation for your lower bound.
Yeah. So let me address the last question first. The error rates, we could certainly derive some estimates of those error rates by looking at the Taylor expansion remainders that we've developed, right?
Mm-hmm.
The problem is that in order to evaluate those, one would have to have plug-in estimates of those quantities, right?
Right.
Which we don't have yet, because those remainders depend upon the unknown
true parameters. No?
Right.
Yes, something you don't know.
Yeah. So that's why we've been focusing on here sort of a standard resampling type of estimate of these error rates, which I showed in these histograms, right? Like the histogram here.
I see.
And so that leads me into the answer to your first question, which is that each one of these. So the way we generate this number is we divide the sample into a training and validation sample.
Mm-hmm.
Right? And in this particular case, I think it was like a threefold cross-validation, right? And then we randomly select that 2/3 and compute this benchmark, right? And that's how we generate this histogram. And then we take the mean of that. So in a sense, this matches the way that these other methods have been developed, because they also report average error rates over a trained validation set, right? So these aren't just for a particular test set.
Okay, I see.
So they also use, to the best of my knowledge, they use also the average over a bunch of test sets, right?
I see.
Right. And of course, if they only used one sample from the hundreds that we're using, well, then the number they're getting has some variance, some variation, right? And maybe that variation might be enough to pull it down to our benchmark, possibly. But the fact that all 4 of them are above the benchmark indicates that they're probably not using the most favorable sample. It truly is a representative of the performance.
Okay.
But it's a very good question, because when it comes right down to it, and you look at these papers, it's never exactly clear how they're computing these numbers, right?
Yeah.
And so,
computer. But of course, I think that your explanation is clear. This is full of convincing results. Thank you.
Yeah, you're welcome.
Other questions?
Hey, Al, this is Jeff Fessler. Nice talk.
Hi, Jeff.
On classification here. So of course, you know well that there's problems like non-parametric regression that also have trade-offs between bias and you do a similar clever combination of estimators with different effective bin widths or whatever to to get a free lunch, so to speak? You know, get to beat the usual rates or whatever? Or do you need to start with a problem that has these terrible rates to begin with?
Yeah, I think it's similar, because in these regression problems, you may not, especially if you're talking about nonlinear regression, right? So you're trying to find a conditional mean, right?
Yeah.
And you don't know the distributions, so you're back to the sort of the same problem of not having, of having terrible estimates of the distributions themselves, plugging them in to get to the conditional mean estimator. So I think you could apply this to that problem. We haven't done that yet.
Okay.
I strongly suspect that you can get the same results. The critical thing throughout this is simply, and I didn't emphasize this for lack of time, is that there's a hidden assumption here, right? To get all this to work, as anyone who's ever done any asymptotics knows, you can't do asymptotics unless the quantities that you're taking asymptotics with respect to are differentiable, right?
Okay.
So we had to take D derivatives. Remember that in our Taylor series, it was up to order D. So that means that all the distributions have to be D times differentiable, at least, right? That may be a strong assumption for certain applications.
D is the problem dimension here. The D was.
What's that? And if D is right, and if D is large, that becomes a much more stringent condition. What we do in order to compute, in fact, and I didn't explain this either, for when D is large, and like here at 784 dimensions, we actually don't compute the benchmark in 784 dimensions. We compute it in a lower dimension.
Okay.
Right? An intrinsic dimension. So you can look at it as you do PCA on the data, and you cut it down to a manageable number, which I think we've generally been around 20 to 25 dimensions. And so that intrinsic dimension, you can construct the benchmark. The benchmark is a little bit conservative in that case, because right, you've projected away potentially some informative dimensions.
Right.
It's not a panacea for everything, right?
Very interesting. Thanks.
Yeah, you're welcome.
Hi, Dr. Hero. I have a simple question here. Have you tried applying the epsilon ball estimator to the most misclassified Mnist images?
The most misclassified. So
say if you apply the state-of-art neural net to Mnist and then find say that 10% of the images that is the mostly wrongly classified, and then just apply the benchmark learner to this subset of the data and see what kind of error rate you will get.
That's an interesting suggestion, right? And that will give you an error rate, of course, that's dependent upon the classifier, but it also might tell you, it might inform you that if that error rate is actually smaller than what's reported by the classifier, that there's maybe a solution which would involve some sort of hierarchical classifier, right? You look at you implement the first classifier, and if you have a confidence score, which most classifiers do, on how well they're classifying, and you can match that score to the poorly classified examples, then you could flag those examples and then apply a new classifier to the ones that have been poorly classified, right? And the benchmark learner would tell you whether that's possible or not, right?
So then we can use the benchmark learner to get a sense of how confident we can be about our best performing classifier before.
Right. Indeed. I mean, if the benchmark learner says that a Bayes classifier should be able to classify these with very, very low probability of error, then it tells you that the classifier you're using somehow is not balanced, right, over the entire set of instances, and can be potentially greatly improved. And moreover, if there's some sort of common attributes to those misclassified images, then maybe you could say something about the classifier, and maybe even say something if you this sort of goes back to the question that Jean was asking, except instead of looking at sort of the most important variables, you could look at sort of the most important instances, right? So take your data set and divide it into those that are easy to classify and those that are difficult to classify. And if you have a if you have a submodular objective function like mutual information or some other bound, then you should be able to use a greedy technique to basically construct a continuum of images that are harder and harder and harder to classify, and then you get to some point, and the ones that are really hard to classify, maybe those are the ones you concentrate on because the other ones are easy, right? Relatively speaking. And you try to build a classifier just for those really hard ones, right? Sort of similar to the sort of support vector concept or the boosting concept, right? Where you try to identify those most difficult to classify instances that give you the most gain, right, in your error.
Thank you.
Yeah, nice suggestion though. Yeah, we hadn't thought of implementing it that way.
I have a couple questions. One of them is just, do you know what the human error on the Mnist data set is?
I don't offhand, no, but it's a good question. Yeah.
Yeah, I'm curious if it is lower than your prediction. Looking at it, sort of, I think, well, I can tell all those numbers apart. So
yeah.
And then, so that sort of brings the question, like, is the human error lower than the Bayes optimal?
The Bayes optimal error, right?
Yeah. And then what does that mean?
Right.
Yeah.
That could mean many different things, right? I mean, it could mean that there's much more contextual information that we bring in, that the priors, we have much better priors, right? The priors, incidentally, I didn't mention this in the talk, but the priors are estimated using maximum likelihood. So that's just the relative number of instances in each class. But that might not be what we're using as humans, right?
Right. And I suppose humans actually, it's unfair to say that we're trained on this data set. We've been trained on millions of numbers that we've seen.
Right.
So that's
right.
It's a little bit of an unfair comparison.
Yeah. No, absolutely. Right.
My other question is, have you thought about, or what would be the extension of this to predicting a continuous outcome?
A continuous outcome?
Mm-hmm.
Yeah, I mean, that's sort of gets back to Jeff's question. We've looked at this. We actually have a paper that appeared a few years ago that doesn't use the ensemble idea. It basically constructs a non-parametric estimate of the Fisher information matrix, right? And so if you have a distribution, it's a regular family, smooth, differentiable, not a full rank Fisher information matrix, then what we showed in that paper was that you could construct an estimate of Fisher information by using these divergence estimates and the fact that the Fisher information is a information divergence when the distributions are really close, right? So it's an approximation, the divergence for very close distributions. So if you perturb the data a little bit, then you make the distributions close, and we're able to then derive these gradients and then compute a non-parametric estimate of the Fisher information. But we haven't thought of applying ensemble methods to that.
Mm-hmm.
Yeah, and we haven't done the analysis of bias and variance either. So we really don't know what the bias and variance behavior for that problem is. I suspect, as I was saying in my response to Jeff's question, that it's also very poor because you have high dimension, and you're trying to estimate. We have a bias that's due to finite difference estimation of a gradient. You have variance that's, of course, due to the limited sample size. So I'm sure there's an equivalent story there, but I don't have a student right now who's interested enough or smart enough to tackle that one.
Sure.
Right.
Thanks.
You're welcome. Great questions.
So your current framework is based on the generative model framework that you given the label, marginal label distribution, and given the label and the model the density of each class, right? So of the predictor in each class. So do you think we can do the other way, like just using discriminative modeling framework that directly model the probability of y given x, and then you can avoid to estimate the density, right? So you can basically just estimate the function.
Right.
But yeah, of course, maybe that's gonna have other challenge issue there. Yeah, I just would like to hear your comments about that approach.
Yeah, I mean, in a sense, right. I mean, what you're saying is if you make a transformation on the distribution, right, then you could, in principle, go after the posterior distribution as opposed to the conditional distribution given label, right?
Right.
And I guess I don't know how to do that offhand. How to form a kernel estimate of the posterior distribution directly without having to estimate the marginals and all that, because I mean, one way to do it would be to just use the plug-in estimator for in Bayes' rule, right? So, but that I don't think buys you much.
Right.
Is there a direct way to do that? Is a good question, and I can't think of an answer right now that would enable one to directly estimate the posterior probability, unless you have some ideas on doing that. I don't see how that would simplify it.
Idea. Sometimes I was thinking that maybe you can use neural network to do that, but that's going to involve another sort of type of neural network training. You basically can model any nonlinear function using neural network, right? But the formulation may be different from the classification problem. Maybe you focus on this benchmark learning problem, but that also involves how you justify your method is flexible enough can estimate this benchmark estimator. I mean,
it's a great question. Yeah, I mean that raises, because we have not yet compared the benchmark to autoencoder, generative or discriminative models that actually generate a posterior distribution, right? I think that would be an interesting comparison. That if it could indicate to what extent the deep network of autoencoder, generative autoencoder, let's say, to what extent is that actually approximating the Bayes optimal estimate, right?
Yeah. That could be an alternative way to do that, but I don't know. I mean, theoretical analysis can be very difficult, I think. That
yes.
the difficulty of the deep learning theory. But in practice, maybe that they also can produce some reasonable estimator, right? So that's and also I think the generative model in general is harder to ask a classifier, right? So if we're just thinking about build up classifier, we probably will not go with this way to model the two density and then build up the classifier. That's why usually it's a harder problem than you directly model like a build up classifier based on the probability of y given x, right? So that will be easier problem to handle. But estimate error rate is going to be the complete different story. Yeah, I agree.
That's right. Yeah, and it'd be interesting to look at some, like fiducial version of this this benchmark learning problem where where the likelihood doesn't even exist. It's just all you have is the posterior, and and you go after that directly using who knows what. But one of the attractive things about this approach, the way it's developed here, is that it's actually quite simple, right? Much more straightforward to analyze and to implement and to train than a deep network, right?
Absolutely.
And plus we can get these. We can relatively easily get these histograms, because it runs fast enough that we can run resampling hundreds or thousands of times, right? You can't do that with a deep network.
Absolutely.
You can't retrain a deep network hundreds and thousands of times.
Right.
But it's certainly worth thinking about. I think another aspect is, and this is a question that's been asked of me several times in the past, is does the benchmark estimation problem that I've just presented here lead to any insights about improving the classifier, right? Right. And it's sort of at a similar level of what you were describing a minute ago about a generative model implemented maybe by a neural network, maybe by some other method to estimate the posterior. Once you have the posterior, then it's a trivial task to estimate the Bayes error rate. So there's certainly in this ensemble method, you can certainly map that to this weighted ensemble method. You can map that back to ensemble estimates of the likelihood ratio. Right?
I see. Yes, that's right.
So So if you could translate this into, if you could find an equivalent formulation in terms of estimating the likelihood ratio as opposed to estimating the performance of the Bayes classifier, and those aren't equivalent, but maybe they're closely related, then this would have direct impact and influence on improving our estimates of a classifier, actually coming up with a better classifier in addition to having a benchmark.
Yeah, that's right. Yeah, that's a very inside comment. Yeah. Thank you.
Yeah, you're welcome. Yeah, great comments.
Any other questions? Okay, well, in that case, we will wrap up. Thank you so much for speaking and then talking to us afterwards. It's been
great.
a great
pleasure. Very enjoyable. I enjoyed your questions, and I enjoyed meeting with several of you earlier. And I almost feel like I'm back in Ann Arbor. I'm on sabbatical in Boston, so it's nice to reconnect.
Great.
Very good.
Well,
Thank you.
thank
Yeah.
you so much. Take care, everybody.
Thank you. Bye.